Alright, so starting off with the 1998 BC Frq, number 1. So we are supposed to let R be the region in the first quadrant, bounded by this graph, y equals 8 minus x to the 3 halves power, the x-axis and the y-axis, and then find the area of region R. So first let's graph roughly what this looks like then. So at 8, we've got area that would look something like this. So at x equals 0, we're going to be at 8, and we're going to keep getting smaller and smaller from there in some sort of a curve, right? How can I get 8 out of this? So if 8 is equal to x to the 3 halves power, and then x would be equal to 8 to the 2/3 power, and so that's 4. So we've got a graph that looks something like this. The point here at 0, 8. And a point here at 4, 0. Okay, somewhere on the inside we've got region R. I want to find the area of region R first. What do I need to do to get this area? Okay, let's go ahead and start with Kyle. So I want to find the area of region R. We are bounded by the x-axis, the y-axis, and our graph of y equals 8 minus x to the 3 halves power.
Oh, I'm on mute. A is equal to the integral of 0 to 4 of 8 minus x to the power of 3 over 2 dx. And if you plug it in to your graphing calculator, I did that, I guess you get the area is 19.2.
Okay, let me check really quick because I don't... Okay, a graphing calculator is required for this, so we do have access to a graphing calculator. So let me go ahead and run that really quick. I'm going to throw this into our y equals section, just so I can save it for later. This is 8 minus x to the 3 halves power. And we can cite that later on as y1. If you want to integrate, you can go to math, and then your 9th option down is fn integrate. And this takes an equation, which in our case is going to be our variables, y variables, function y1, a variable, x, from lower bound 0 to upper bound 4. Would match what we've written over here. That should give us an answer. Okay, so we've got 19.2. Okay, for B, I want to find the volume of the solid generated when our region R is revolved about the x-axis. I'm going to jump to Jin for this one first, who I believe is on chat, so I'm assuming is still on chat. Jin, if we are revolving around the x-axis, would this be disk method or shell method, do you think? Okay, so Shell method normally we'd use to revolve around a vertical line. The x-axis is a horizontal line, so in this case, I think we would use this method instead. Let me draw out what this looks like. So this is something like this, if this is our region R. I'm going to take our region R and some sort of radius and use that to spin about our axis of rotation in order to create a disk. That disk will have an infinitely small width, which I'm drawing here in yellow. What is that distance of the infinitely small width? Jin, what is the distance of this space here in yellow? That infinitely small width of the cross-section that we are spinning to create this circular disk? So I've got an R and I've got a distance here in yellow. Jin, what's our distance here in yellow? Okay, I think we may have lost Jin, so I'm going to jump over to Andrew, I believe you still got here. Yes. Andrew, what's our distance here in yellow?
dx.
Okay, our distance is dx. And then what's my radius? That's our distance here in black.
That's our function.
Our function,
Of x.
which in our case is 8 minus x to the 3/2 power.
Yes.
So my radius is 8 minus x to the 3/2 power. If I wanted to create the volume of the disk that we have formed so far, then I would need an area, and I would need to multiply that times the width. What's the area of the circular cross-section right now?
Two pi the integral of 8 minus x 3 over 2 power.
We're close. So 2 pi r would give us a circumference as the distance around a circle.
So pi times the integral of 8 minus x 3 over 2 function to the power the square. Yes.
Okay, so to the power of 2 or squared. And we are integrating from what to what? Make this a little bigger.
From 0 to 4.
Okay, we are integrating from 0 to 4. Okay, that's good. And then I'm going to multiply by our infinitely small dx, which will make this 3-dimensional instead of 2-dimensional. So now I've got r times dx is 3d. Okay, I'm going to move this out of the way. As well. And that should give us our volume of what happens when our radius is revolved around the x-axis. again and again and again and again in order to eventually spin the entire area R about the x-axis and create a 3D shape. Kyle, can you tell me what that shape would look like in 3D?
It would look like a semisphere, like half a ball, half a sphere.
Yeah, so like half of an egg almost, yeah. Okay, I do need to find the volume, so I'm going to do the same thing that we did last time and just throw this into our graphing calculator. Again, we've already got 8 minus x cubed stored as y1, so we can shortcut a little bit. So, actually before I do math 9, let's go ahead and multiply by pi. So this will be pi times math 9. I'm going to integrate our variables, y variables, function y1 squared in terms of x from 0 to 4. And that should give us our volume. Okay, so that's 361.911. And the last one. A vertical line x equals k is dividing the region R into two regions, such that when they are revolved around the x-axis, they generate solids that have equal volumes. I want to find the value of k. So in this case, we still have our same shape, but now we're saying that there is some value here, x equals k, such that when we split up all of our shells that we are spinning around, in order to create our 3D shapes, the volume of the first part after it's spun will be equal to the volume of the second part after it is spun. Andrew, I'm going to jump to you. If we're going to split this volume in half, then what should the volume of each half be equal to?
The volume of the semi-sphere divided by 2.
Okay, so I could take our volume that we got in part B and divide by 2. So I'm going to write that for now. Volume of the whole over 2 is equal to, now I need an equation for the volume of the first half, we'll say. So what should our equation of the first half be?
Oh, is it still me? Then should be pi over 2 times the integral.
Okay, I think you're giving me this side again.
Oh,
We've already divided the whole by 2, so I want a new equation for just the area from 0 to k.
Pi times integral of 0 to k, parentheses 8 minus x to the 3 over 2 power square dx.
Looks good. All right. So now we just need to solve this. I'm actually not sure how I would do this in a calculator, so I'm going to go ahead and solve this by hand, I think. We had our whole volume last time, which I wanted to divide by 2. So I had 361.911, which I think I still have in the calculator, so I'm going to divide that by pi and see if that's a multiple of pi, because it should be in the end. We'll see what that looks like without the pi in it. Okay, so that's 115.2 times pi. So I've got 115.2 pi over 2 is equal to. Then I'll go ahead and square this. We'll integrate, plug in our upper bound as k, subtract our lower bound as 0, and then actually solve for k. Kyle, what happens if I square 8 minus x to the 3 halves power?
We get 8 times 8, 64 minus x cubed.
Okay, there will be an x cubed, so x cubed. But I do have a middle term as well.
Forgot. X, so x times k. Wait, write this down. X times x 3 over 2 minus. Oh, wait, so it's negative. So is it minus 16x 3 over 2?
It is, so minus 16x to the 3 halves power. And then we're going to integrate, so we're going to add 1 to each of these powers, divide by the new power. We'll plug in our upper bound minus lower bound and see what happens. This is 115.2 pi over 2 is equal to pi times 64x. Let me go ahead and grab somebody to integrate. Jen, I'm going to have you go ahead and integrate the rest of this for me. So what happens when I integrate negative 16x to the 3 over 2 power? Or x to the 5 over 2. Okay, we're pretty close. So your power is right. I am going to add 1 to the power and get 5 over 2, but I'm also going to divide by the new power. So this would be negative 16 divided by 5 over 2. If you're dividing by a fraction, you can flip and multiply. So I'm going to end up with a fraction. And I think you're typing it out, so I'm going to wait. 32 over 5, perfect. So minus 32 over 5, x to the 5/2 power. Plus, last one, gen one more time. Integrate x cubed, and we get x to the 4th over 4. Okay, I'm going to jump over to Kyle and we'll finish this off. So Kyle, I need to plug in my upper bound, subtract my lower bound. I can also take out our pi from both sides, since I've got that multiplying through everything on both sides. So for our next step, what's going to happen when we plug in our upper bound and subtract our lower bound for the right-hand side?
We get 64k 115.25. Oh yeah, 64k minus 32 over 5 times k to the power of 5 over 2 plus k to the 4th power over 4. And I guess since it's 0, I think that's it.
Right, so our lower bound is going to completely cancel out. Okay, so from this point, I think I would just plug into a graphing calculator since we can solve any equation with a graphing calculator, and that way we won't have to worry about trying to simplify this into something that can factor evenly. So let's go from here. I'm going to set my first line equal to 115.2 divided by 2. And we'll set our y2 equal to 64 times x minus 32 over 5 x to the 5 over 2 power plus x to the 4th over 4. Okay, then I'm going to graph both of those equations, and we'll figure out when they meet. Okay, so that's a little bit too close in order for me to see when they're going to meet, so I'm going to change my window size. And let's try from -1 until +1, maybe? We'll graph it again. Two over 2, we've got 64 minus 32. Let me try just calculating intersect right now. Okay, so we do have an intersect even though it's right on the edge of our screen and I can't see that. I'm going to try to change the window so that I can see that intersection again. Let's go up to 100. There we go. 115.2 we've got to hit. Okay, so second calculate and intersect of the first curve, the second curve, and a guess. And that should give us our intersection up here. Okay, sorry, we intersect at 0.995, which should be our value of k. All right, any questions on what we did here? Okay, I'm going to check really quick and see if the number 2 is also on the AB test or if there's something similar. Number 2 is on both. Okay, so we'll do this one together too. So for number 2, I want to find the limit as x approaches negative infinity and the limit as x approaches positive infinity of this function. So first, Andrew, what's going to happen if I plug in negative infinity right now for our limit?
Then we'll approach 0.
Okay, so this will give us 2 times negative infinity e to the 2 times negative infinity, which is, you're right, 1 over infinity times negative infinity. But that exponential power is going to grow a lot faster than our polynomial. So in this case, we will approach 0. And Jin, over to you. If I take the limit as x approaches infinity of 2x e to the 2x, what will happen? Infinity, okay. I think I'm hitting something as I try to write on the screen. It's stopping me from writing. There we go. Okay, so infinity. And I want to find the absolute minimum value of our function. And then justify that our answer is also an absolute minimum. Okay, what do I need to do to find the absolute minimum of this function, Kyle? How do we find a normal minimum? So, relative minimum or maximum? Might still have you muted if you're trying to speak. Kyle, can you hear us?
Hello.
Hey. Okay, there we go. Okay. So what do we need to do in order to find an absolute minimum?
I'm not quite sure.
Okay, jumping over to Andrew. In order to find a minimum value, what do we need to do?
Derive 2x e to the 2x power and set it to 0.
Okay.
And then find if the value is greater than that x. Oh no, never mind.
Got the first part. I'm going to jump back to Kyle. So I need to get the derivative. In order to figure out whether we have a minimum or a maximum, we can take a look at the slope. Kyle, what should the slope be equal to if we have a minimum value that is a relative minimum or a maximum value that's a relative maximum? So what would the slope be at a relative minimum? Okay, I think you said it, sorry.
Negative infinity?
Not negative infinity, no. Relative minimum would look something like this. So what would the slope be at the relative minimum?
I think there's something wrong. I think there's something wrong with my connection. Did you draw something? I think it's my
connection. I'll try turning my video on and off really quick. So here we go. Okay, let me know if you can see. Relative minimum would look something like this, sort of like a U shape, and we would be at the bottom of that U. So what should the slope be? Okay, maybe still having connection issues, but at a relative minimum or maximum, any relative extrema, our slope should be 0. So we're going to go ahead and derive f of x and set our derivative equal to 0 to figure out when our slope will be 0. Let me just copy f of x for now so I can zoom in. This is 2x e to the 2x. Jane, what happens when we derive? Close. So we need a product rule for this. So we have two functions here. Kyle, I'm going to jump back to you while Jin's typing. What's going to happen when we derive this?
You you get 2 times e to the power of 2 over x plus 2x e2x times 2.
Okay, Andrew, over to you. This slope needs to be equal to 0 if it's going to be a relative minimum. So if I set my slope equal to 0, is there anything that we could factor out, or how would you solve this?
How would I solve this?
Yep.
I used graphing calculator.
Oh, okay. That's okay. I think I still have a calculator for this one, so that would be fine. Yeah, I do. I'm going to go ahead and pull this out for me personally. So this is 2e to the 2x, 1 plus 2x. And if that's true, so anything raised to a power cannot be equal to 0. So if it's a negative number, we'll end up making it a fraction. If it's a positive number, it just gets bigger, and if it's 0, it becomes 1, right? So right now I've just got 0 is equal to 1 plus 2x. And so what should x be in order to make this equal to 0?
negative 0.5.
Perfect. X is negative 1/2. Okay, so if I was just looking for a relative minimum, then I could prove that this is a minimum by checking the slope around it to say our slope changes from negative to positive about that point, and that would be enough proof to prove it was a relative minimum. But because they asked for an absolute minimum value, we don't just need the relative minimum, the smallest relative minimum on the interval. We need the smallest point on the interval, even if that point doesn't have a slope of 0. So I need to do a little bit more testing with this. But we'll test our slope first and prove this is a minimum. And so about the point negative 1/2, I want to know what's happening to our slope. So Kyle, if I plug in -1, will my answer be positive or negative?
It'll be negative.
Negative. Jin, if we plug in 0 right now, will our answer be positive or negative? Okay, if we plug in 0, our slope will be positive. So that means this is a relative minimum. In order to prove that it is the smallest y value on the interval, though, then I also need to test the start point and end point of any intervals that we had. Now, in our case, I don't think they gave us an interval, though. They did not give us an interval. So in our case, because our slope is decreasing for all values before negative 1/2 and increasing for all values after 1/2. Then we could say something like this. X equals negative 1/2 is the absolute minimum as it is the only critical point and the slope is negative. Whenever x is less than negative 1/2 and positive, when x is greater than negative 1/2. That should be enough proof that this is the smallest value on the entire function. Any questions on what we did?
For proving the absolute minimum, can we use the limits that we got for part 8?
I don't think it would help. Those limits tell us what's happening at the end of the function. So that proves we keep going up forever. Those limits are going to help us graph our function. I know that I'm going to approach 0, but we keep going down up until we get to negative 1/2 and keep going up after that, right? So we've got some function that looks something like this. But I don't think those limits help us prove what the smallest y value is going to be, unfortunately.
Okay.
If our function looped back around, so if we had a limit as we approach negative infinity of negative infinity, then I would have to have another critical point where we change direction. And I could use that for my proof. Since we only have one critical point, we know we don't change directions ever. For part C, I want to know what the range of our function f would be. And that's maybe a word we haven't seen since algebra. What does the range mean? Just an English vocab thing. Anyone?
The possible values of y.
Perfect. So we're looking for what y values are possible when we say range in English. While I'm here, if I wanted to know what possible x values there were, what could I say?
Domain.
Domain. Cool. So I want to know what possible y values there are for f. So first, looking at our limits, our y values have to be able to go up to positive infinity. And since we know what the absolute smallest y value is, from part B, we know what happens when x is negative 1/2. What could I do in order to figure out what our range would be? I think Jin was typing and then stopped. So, Kyle, how can I find the range? We know our smallest possible y value from part B. The absolute minimum y value happens when x is negative 1/2. What's the largest possible y value?
Infinity.
Okay, largest possible is infinity from part A. So our range must be between whatever f of negative 1/2 is and infinity. So I'm going to write that first, and then we'll solve for the numbers. So our range must be including f of negative 1/2 to positive infinity because of our limits. And now we need to figure out what f of negative 1/2 is. So I'm going to plug in negative 1/2 into our function for f up here. I'll do this in a separate step, I think, because that's a little bit cleaner. Kyle, back to you. What happens here?
Do we just solve it?
Yes.
To the power of 2. You get negative 0.367.
Okay, you're right. If I was going to do this without a calculator, this would be negative 1 times e to the negative 1 power, right?
Yes.
Or negative 1 over e. Okay, so if I want to write my range, then I could say that our range is including negative 1 over e, and then going to infinity. Any questions on our range? Okay, last one. I want to take the family of functions that are defined by y equals bx e to the bx, where b is a non-zero constant, and prove that the absolute minimum value is the same for all non-zero values of b. Okay, so we're going to do the exact same thing that we did last time. And find the absolute minimum value of the general form, y equals bx e to the bx. I'm going to see if I can write over this. And just have to remember not to erase. On any of those tiles. Okay, so for part D, and for y is equal to bx e to the bx, I want to find the absolute minimum. Alright, Kyle did the deriving last time, so Andrew, over to you. What happens when I derive y equals bx e to the bx, where b is some non-zero constant?
Y prime is b e to the bx power times plus b squared e to the b squared x e to the bx power.
Perfect, so that b squared is because you had bx e to the bx times b with chain rule, and that became b squared. Okay, so I would want to set this derivative equal to 0 and then solve for x. Since we cannot do this in a calculator this time, we'll have to do it by hand. So jumping back to Kyle again, actually jumping to Jin, because I think we can type this part. Jin, is there anything that is in common that we could factor out of the right side? B e to the bx. Okay. So that leaves me with b e to the bx times 1 plus bx. Okay, Kyle, over to you. I want to solve for x, so what do I need to do?
You could cancel out bx.
I can cancel out b e to the bx because no matter what value there is for, no matter what value I plug in for x, there's no way for this left side part to equal 0. If we plug in a negative value, then I end up with a fraction, and it still won't be 0. If I plug in 0, it'll become 1, and if I plug in any positive value, it'll just get bigger. So because the left side cannot ever be 0, that means the right side is the only part that could be 0, so 0 must be 1 plus bx, where b is some constant. So if I want to solve for x, what do I need to do?
Just subtract 1 and divide by b. So x is equal to negative 1 over b.
x is negative 1 over b. Perfect. And then if I want to find the absolute minimum value then, first I'll do a first derivative test with that in order to prove that that was actually a minimum. So negative 1 over b, where b is some non-zero constant. We were told it was positive, right? Non-zero constant. We were not told it's positive. Okay. If I plug in... If I plug in 0 right now, I get a positive number. If I plug in negative 2 over b, which would be a number that is less than that, then I'll get 1 minus 2 times some positive number, would be negative. So this is a minimum. And now that we've proven that this is the minimum, and our function is continuous with only one critical point there, and this will also be the absolute minimum, and we just need to find the y value. So very last step, Andrew, how do I find the y value?
Plug in 1 over b, negative 1 over b for x. For bx e to the bx power.
Okay, you're right. So this first part proved it was a relative minimum, but there are no other critical points. So therefore it must also be an absolute minimum. And Andrew, right, I'm going to go back and plug in negative 1 over b for x in order to get the y value. So my y value when x is negative 1 over b should be equal to what?
1 over e. Negative 1 over e.
Right. Which is the same value that we got last time. Negative 1 times e to the negative 1 power, or negative 1 over e. All right. Any questions on what we did for any of this? Okay. I'm going to go ahead and break here for the AB students because we're averaging about one of these every half hour with all the pauses. And we'll do one more calculus BC only FRQ. And we'll call it a day for there, I think. So, Jin, thank you so much for coming. If you want to leave, you can. If you want to stick around for the BC problem, you can. It's up to you. All right, so taking a look at our next one. So I think number 3 is Taylor series. We already did 3, I think, so I'm going to skip to the other BC only one. That one's both. That one's both, I believe. Okay, I'm checking my notes really quick. So AB number 6 was... different. Okay, so this is the other BC one. Alright, so for number 6, we've got a particle that's moving along the equation y equals x cubed minus 3x. Our x coordinate satisfies this differential equation. Dx over dt is 1 over root 2t plus 1 for all t greater than 0, with the initial condition x at 0 is negative 4. So when t is 0, x is negative 4. Okay, first I want to find xt in terms of t. Starting with, I believe Andrew finished off the last one, so starting with Kyle.
So we should first integrate dx over dt to find x.
Okay, so I want to integrate in order to find x. Before I can integrate, though, I need to do one step first.
Find the u.
Before that, I've got a problem with my integration because we've got mixed variables on one side.
I'm not sure what the first step is.
Right now on the left side, we have both x's and t's. So I need to change that.
Do we move dx to one side?
I would, but to get dx alone, I can actually leave it on the left side because it's already on top. So I'm going to move the dt. So this will be dx is equal to dt over square root 2t plus 1. Okay, and now I could integrate both sides, since we only have one variable on both sides.
Okay.
Okay, so from here, now we can keep going and start doing your u substitution stuff. What would your u be for this right side?
2t plus 1.
2t plus 1, that means u prime must be
2.
2 dt, okay. So that is the right power of t on top. So when I rewrite this right side, what will the right side look like?
The right side will look like u to the power of negative 1/2. 1/2 times u to the power of 1/2.
Okay, that's good. So you took that 1/2 because your u prime needed a 2 and you didn't have one. So 2 times the 1/2 gives you just dt. Recapping for the video later. I cannot draw an integral sign from this angle. There we go. Andrew, what's going to happen when we integrate both sides?
This will be x equals 1/2 u to the 1/2 power.
Okay, you added 1 to the power, and I need to divide by the new power?
Times 2.
Times 2, perfect. I also didn't put a plus c on the other side, so I'm going to throw a plus c on this side. Since we are integrating indefinitely for now. Okay, so that leaves me with x is equal to u to the 1/2 power, or the square root of u plus c, where u is equal to 2t plus 1. So this is the square root of 2t plus 1 plus c. Okay, now we can go and look at our initial condition. When x is 0, when t is 0, x is negative 4. So we'll use that in order to solve for our c, and then we'll have an equation for x. So x at 0 equals negative 4 is what we were given. So therefore, if x is negative 4 when t is 0, then we can solve for c. Kyle, back to you since you're next. What's going to happen when we solve for c?
Since 2 times 0 is 0, plus 1 is 1, the square root of 1 is 1. So we subtract 1 from both sides, so c is equal to negative 5.
Okay, and that leaves you with x is equal to the square root of 2t plus 1 minus 5. Gives me a general form for x at any value of t. Any questions on part A? Okay. Moving to B. I want to find dy over dt in terms of t. We were given y is x cubed minus 3x. So in this case, Andrew, if y is x cubed minus 3x and x is square root 2t plus 1 minus 5, then what is dy over dt? Let's get a general form over here first, maybe.
3x squared minus 3.
Oh, 3x squared times chain rule.
Times x prime.
You're right, but it matters what we're deriving in terms of. So I don't just want to write x prime for this one, because x prime...
dy over dt. Dx over dt.
Dx over dt, okay. So x prime would refer to the derivative of x in terms of t, not the derivative of x in terms of x. But since we've got parametric equations here, and x prime could mean both, I think I'm going to prefer this form so we know which x prime we're talking about. Okay, and then you said minus 3, and then we're going to have chain rule there as well. So minus 3 times
dx over dt.
Dx over dt. Okay, so that means I need to know what dx over dt is before I can know what dy over dt is. So I'm going to jump over to the other side. Kyle, over to you. If I want to find dx over dt, what's going to happen?
Same thing as. So I know that if we simplify it, it's dx over dt times 3x squared minus 3. So we divide 3x squared minus 3 from both sides.
Hold on, sorry. 3x squared. Okay, I think you might not have video again. So we're looking at a different formula at the moment. I'm going to paste a picture to the chat really quick. Oh, hey Eric, didn't notice you come.
Hello.
Okay, so with chain rule, that was 3x squared times dx over dt minus 3 times dx over dt. Kyle, are you able to see the picture or the video? Kyle, do you have a picture that was sent through the chat or the video on screen?
Yep, I'm able to see it now.
You're able to see it now. Okay, so if x is the square root of 2t plus 1 minus 5, then what is dx over dt?
1 half. 1 half times 2t plus 1 to the power of negative 1 half times 2.
Awesome. So that 2 and the 1 half will cancel. So that means we're left with just, because this is a negative power, that's 1 over, and because it's a square, 1 half, this will be a square root. So this will be dx over dt is equal to 1 over the square root of 2t plus 1. Okay, so that means jumping back to our other side. Eric, what's our answer for dy over dt?
Plug in the numbers.
Need to plug in the numbers. I've got a lot to plug in actually. If I factor out that dx over dt first, that'll give me this 3x squared minus 3, right? But I do need to substitute for x as well as our dx over dt, so I can get dy in terms of time, only in terms of t. So what is dy over dt?
1 over root 2t plus 1 times 3 root 2t plus 1 minus 5 minus 3, so minus 2.
That's 3. Okay, so something like that. I don't believe they said anything about needing to simplify, so now that we're in terms of t, I can just leave it there, and I should be able to get full credit. So I actually don't want you to simplify from that point. And the reason why is because if you make a mistake in your simplification, you can actually lose points. So here is fine. Okay, then for the last one, we were asked to find the location and speed of the particle at the time t equals 4. So first, what do I need to do if I want to find the position? Andrew.
The position. I should find x and y.
Okay, so we need x at 4 and y at 4.
Yes.
Okay, we have our x equation from part A, root 2t plus 1 minus 5. So what is x at 4? Still with Andrew.
-2.
Okay, so this is the square root of 9 minus 5 is -2. I also need my y position. Nope, I don't have quite as much room as I thought. So y is equal to x cubed minus 3x. So assuming our x is correct, we can just plug that in. So our y when t is 4 would be equal to what?
-2 as well.
Okay, so I've got -8 plus 6 or -2 as well. So at t equals 4, the position of the particle is -2, -2. Okay, a little bit harder. I want to know what the speed of this particle would be. What's the equation for the speed of a particle? Or how can I find the speed given this information? Right now we know dx over dt and we know dy over dt. But that's really our horizontal velocity and our vertical velocity. If I want to find the actual velocity, what do I need to do?
Hey, is it my turn?
Open to anyone right now.
Oh, okay. Okay. So use the derivative of x and y.
I am going to use the derivative of x and y. What would my equation look like? So I need dx over dt and dy over dt, but once you've got them, how do you get the speed?
We find the value of dx over dt first, and then we input it into dy over dt.
Okay, that would give us a horizontal velocity and a vertical velocity, but once we've got horizontal and vertical velocity, how do we find the total velocity?
we use a parameter like the Pythagorean theorem.
Pythagorean theorem, perfect. So my general form for speed is going to look something like this. Speed would be equal to the square root of dx over dt squared plus dy over dt squared with Pythagorean's theorem. So that does mean I need to find dx over dt and dy over dt first. So looking at dx over dt first, because that has an easier equation, dx over dt, we said earlier, was equal to 1 over 2t plus 1. 1 over, square root 2t plus 1. At t equals 4, what is our horizontal velocity? I think we're up to Eric.
One third.
1/3. I'm going to stick with you for vertical velocity as well. Dy over dt was equal to this equation. Dx over dt times 3x squared minus 3. So sticking with Eric, what would dy over dt be equal to, or what are you plugging in?
Plugging in 1/3 for dy, dx over dt, and plug in x. X is 2.
X is -2.
Negative 2.
Okay, so what should our final answer be for the vertical velocity? Three. So that means for our final answer for the speed then, our speed is going to be equal to the square root of 1/3 squared plus 3 squared. Or 1/3 squared is 1/9 plus 3 squared is 9. So this is the square root of 1/9 plus 9. What's my common denominator? Or what is 1/9 plus 9 if I want to write this as a fraction inside? Anyone?
82 over 9.
82 over 9 underneath the square root. If I want to simplify for your SAT or AP exam, this would be what?
Square root of 82 over 3.
Perfect. Root 82 over 3 would be my speed. Because they did ask for a speed, not a velocity, even though taking that square root would make it positive or negative, we don't care because speed does not have direction, so it must be positive. All right. Bit of a long one, but any questions on 6? Okay. Thank you guys so much for coming. I'm going to hopefully finish off the rest of our free response questions next class period. We've got really 2 left because we already did 3. And then I'll start looking at some of the graphing calculator problems from 98. I will see if I can post this to YouTube as well. Thank you.
Thank you.
Thank you.
Bye bye.
Bye.
Bye.